In the remaining videos in Module 5, the focus will be failure in deviated wells. So that's wellbore breakouts and drilling-induced tensile fractures, but in deviated wells. So this is not a vertical well, and the Kirsch equations do not apply. The equations become way more complicated, lots of geometrical calculations, and actually the results I'll be showing in the rest of the module will be coming from simulators. So the complicated equations have been solved numerically and they generated those results. So I'm going to move relatively fast, and the focus is not trying to develop a simulator but just understanding how to interpret the results. So like in the vertical case, for deviated wells, failure depends on the magnitude of the three principal stresses, as well as the orientation of the well, the orientation of the well bore in relation to the orientation of the stress field. Observing failure in deviated wells is a useful technique we can use to constrain the stress magnitudes like we did with vertical wells. Also, it gives us the orientation of the principal stresses. Precisely, we get the azimuth of SH max. Tensile fractures are expected to be common actually in inclined wells because they just appear to concentrate stresses in a different way. And they are usually identified in the sense that they appear as an echelon sets. And we're going to talk about that. You'll see an image. It's basically like short lines within the wellbore image logs. So we'll see that. They don't affect hole stability like in the vertical case. Very useful to assess the in situ stress states and also the orientation of the SH max. They could be misinterpreted, that's a disadvantage, and they could be misinterpreted as natural fractures. All right. There are a number of aspects of inclined wellbore failure that could be counterintuitive. And like I said, we don't try to interpret this stuff by intuition. We form intuition after we obtain the exact solution to the physical problem. And that's what we do with all these numerical simulators. So again, the results you will be seeing in the next couple slides are coming from numerical simulators that have solved the exact problem for the exact orientation of that wellbore. Keep in mind, the orientation can be in any arbitrary direction, right? Because we choose the orientation such that we minimize the drilling risks. And there's more information, more case studies in chapter 10 of our reference text. So, and this is what the geometry looks like for an arbitrary orientation. And again, it's still the cylindrical coordinate, except that it's no more vertical, right? It's inclined. So r theta z. But this z is not really z, right? It's measured depth, which could be at an inclination. I'm again emphasizing that the Cauchy equations we looked at before don't work for this case, right? The Cauchy equation is limited to vertical wells. And for inclined boreholes like this, we need to rotate the stress. Actually, in the subsurface, the far field stresses also are rotated to align with these new planes of weakness, right? Because before drilling this inclined well, the material was filled up and the stress in this region was borne by the material in that region. But when you take out that material by drilling, then the stresses align with this ball, and so the stresses are rotated to align with it. So now we start out by talking about breakouts, wellbore breakouts in deviated wells. This is how the breakouts look like in just a small vertical well section. right, on the sides, and precisely this will be the direction of what stress? SH min or SH max? It will be SH min. That's where you have the concentration of the compressive stresses, the highest compressive stresses. If it's inclined, then it tilts and it's pretty much aligned with the well bore. All right, so that's the vertical section here. This is the inclined section, and it's inclined. We use something that's similar to the stereo net, but it's actually not stereo net. It's just the projection into a lower hemisphere. That's what it is. So if you are right at the middle, it means the well is vertical. If you are right on the edge, it means the well is horizontal, right? So if you're here, you're horizontal. If you're here, you're vertical. In between, well, how many lines do you have? You have 3, so it's 30 degrees apiece, right? So 30-degree deviation is deviated at 30 degrees, deviated at 60 degrees, deviated at 90 degrees. And where they lie on the northeast, southwest poles is the azimuth of the well, right? The direction in which the well is drilled. So we'll be using this to describe the angle of the deviated well. So we've looked at this before, and now we can see the drilling induced tensile fractures for deviated wells. They still tend to be almost vertical, even though the well is inclined. So when you look at the image logs, they don't show as vertical lines anymore, right? So like we said before, they don't travel very far. They are localized right in that region of SH max. So they're short and they try to be vertical. And this is what they look like. That's what we had called the en echelon lines. So this is how they show in the well-bore images. And this is precisely what it is right here. You see those small flags dipping at an angle? Those are your drilling induced tensile fractures. And again, you don't want to misconstrue them as natural fractures that were there before. We created this just by raising or decreasing mod weight and drilling at specific angles. So this is how tensile fractures show on image logs. Now these are the results from the simulator I had mentioned. That is using all the different angles, the orientation, and solving the complicated equation to come up with the distribution of stresses and how they are realigned with the new with the well-bore orientation. And now we're looking at the results for the Andersonian fault regimes. So in the normal faulting regime, using these parameters, we can calculate the required UCS. Again, this is the UCS required before the well will fail. All right. So we've used the prevailing conditions in the reservoir. We've come up with a Morse circle and we've found the UCS. And so you will need as much value of this to create well-bore breakout. That's what this is saying. So in order not to have well-bore breakouts in this red region, which is the highest value of the required UCS, the rock will need to be extremely strong for you not to have well-bore breakouts, right? So if you want to drill, you would rather drill in this direction, which is what angle? 30, 60, a little bit above 60, let's assume this is 70. You will need to drill a well that's deviated at an angle of about 70 degrees. And in this azimuth, right, north west, about 20 degrees, because you wouldn't form break out easily in that direction. If you drill in this direction and the rock is not that strong, the rock strength is not up to this 100, then the well bore fails. So that's how you interpret these results. The red is the high value. So same deal here. You don't want to drill vertical wells in this faulting regime for the particular angle that has been used, and you will rather want to drill a well in this direction or this direction, right? And at about 70 degrees also, or even all the way horizontal, right? For reverse faulting, same deal. You want to drill in this direction. You don't want to drill in this direction because you will easily form well bore breakouts. Unless you're sure the width of the well bore breakout will not lead to um, drilling problems, then you can probably drill a little bit in this direction so you can observe well bore breakouts, but the width is controlled, and all of that can also be simulated. I mean, the control on the width of the well bore breakouts. And it's important to know that all these results were obtained at a specific depth, right? Because I was saying earlier that this will mean you need to drill the well horizontal. Obviously, you can't drill the well horizontal from the surface, right? So this is stress distribution obtained at a specific depth, and the software will give you multiple of these at the different depths, and for obviously hydrostatic pressure in this case.